All right, so now we go into lesson 6.4, which is on rational equations, but dealing with applications. Now, specifically when we deal with the applications, some of these can be a little bit tricky, but the problem solving technique is actually all the same as we've dealt throughout this unit of Unit 6. Now, some guidelines for solving these problems that we want to be careful with. First of all, read the problem very, very carefully and understand what's being asked. So between these different problems, you're going to notice there's a slightly different outlook on each of them. We want to make sure that we can identify the type of problem and then pull from that. The second piece is going to be introduce a variable to represent some unknown quantity being asked for, whether that's time being worked, speed of some object. We want to be very clear with that. We then want to write an equation given our rational expressions or our ratios, solve the equation, and then lastly state the solution and make sure that they make sense, aka we need to check for extraneous roots, because if there's any sort of extraneous root that might not make sense in these problems, it's very careful to make sure we state those. So let's start off with example 1 here in the applications, which is the following. We have two consecutive even whole numbers that are selected, and the difference between their reciprocals is 1 over 60. Find the two numbers. Now, right away, the first thing we want to do here is let's let x be the first number. How do we get the second number? We go x plus 2. Or to get the next even number, let's say the first number was 2, we would have to add 2 in order to get to the next even number, which is 4. Now, what are the reciprocals? The reciprocal of number x is 1 over x. The reciprocal of the 1 over, in this case, not 1 over, but the reciprocal of x plus 2, or that next even number, is 1 over x plus 2. Now what they said is they said a very specific operation around these. If I take the difference of this number and this number, aka I subtract the two, I'm going to get the 1 over 60. So let's set up that equation here. What we're going to do is right below here, we're going to write it as the following. So it is 1 over x minus 1 over x plus 2 is equal to 1 over 60. Now, a couple of important things to note here. First of all, we need to state the NPVs. That's very, very critical. The other thing we need to do is state the lowest common denominator, or LCD. So I'm going to go right above here. And I mean, you could do this in the margin if you really wanted to. Like, hey, maybe we use this space up here. I'm going to go non-permissible values. X cannot equal, well, from our denominators, it can't equal 0. It also cannot equal -2, because if it's either one of these ones, then it's going to eliminate. Now, the other piece I'm going to write in here is our LCD. Our LCD is a combination of all the denominators, or a product of them. So it's 60 times x plus 2. We take one of each unique factor, write them together. Now, this tells us exactly what we need to multiply both sides by. We surround both sides in brackets. We put on the outside 60 times x plus 2. On the left-hand side, we put the exact same thing, 60x, x plus 2. And again, I probably shouldn't put this bracket here, or else that might confuse us. So I'm going to actually take away these, and maybe I just put a product dot instead. So I'm going to put like a little dot and maybe a dot right here. Perfect. Okay. Now we're going to distribute this 60 times x plus 2 into all the terms. When we multiply it into the first term here, the x's are going to cancel, and this is going to leave us with 60x plus 2. For the second term, we're going to get 1 over x plus 2 times this LCD is going to give us 60x, which is equal to, on the other side, the 60s cancel, and I get x times x plus 2. Now let's expand this out. It's going to become 60x plus 120 minus 60x is equal to x squared plus 2x. What we should do is now we should cancel terms, or combine like terms if possible. I realize that 60x's are going to cancel because I have a positive and negative version of them. And then the other step I'm going to do is I'm going to move the 120 over to the right-hand side to make a quadratic equation. This is going to make 0 is equal to x squared plus 2x minus 120. Now, when we get to this stage of a quadratic equation, we always know that we factor it. And in this case, we can do it by inspection. I'm going to get 0 is equal to things that multiply to make -120, add to make 2. That gives us x plus 12 and x minus 10. There we go. And then from here, we would get the following two solutions. We would get x is equal to -12 and x is equal to 10. And then right away, you want to be thinking, well, they said consecutive even whole numbers, and whole numbers, a -12 is not a whole number. It's definitely an integer, but it's not a whole number. So you're going to cross that one out and write extraneous, because it doesn't make sense for the problem. So hence, what is our solution? Well, we see that our first one is x equals 10, our next consecutive number. If, therefore, x is equal to 10, then x plus 2, or that next consecutive even integer, is the other factor, which in this situation gives us 12. So we can say these numbers are 10 and 12. Okay, now that's one that deals with reciprocals and seeing some sort of sum or difference, and we can get those ones. Now, let's talk about distance, speed, and time problems. Not that we want to divulge into physics at all, but we can use this formula or this basic uniform motion equation to help us solve problems that involve rational expressions. So here's what example 2 says. The average speed of an airplane is 8 times as fast the average speed of a train. To travel 1,200 kilometers, the train requires 14 more hours than the airplane. Determine the average speed of the train and the airplane, aka determine what is x and what is the 8x. So for the first one, or actually before we do that, we want to manipulate this formula just a little bit so that we isolate it in two different variants. One variant would be isolating the velocity or the speed, and we would say speed is equal to distance over time. The other variant of this is where we isolate for t, and that would end up giving us where we have distance over the speed at which we cover that distance. Now, we're going to be using the time one because the time one is most interesting to us, especially when they say it requires 14 more hours and we're talking about things in time. We want to use this time formula. Now, I'm going to go over to my table here. The distance both the train and the airplane have to travel is 1,200. So you want to take a second and just be like 1,200 and 1,200. The average speed, well, the train is going to go at a speed of x. The airplane travels 8 times as fast, so it's going to be 8x. Now, the time, we're going to use these as a distance over speed ratio. It's going to be 1,200 kilometers for the train divided by the speed at which it can do it. Same thing for our airplane, 1,200 divided by the speed at which it can do it, which is 8x. Now what we want to do is we want to set up our rational equation given this setup. Now, we got to be very careful because if you look at these, you're like, which is the term that has to go first? If we're looking for a 14 more hour difference here, then we have to look at this and say, well, the term of time that is the longest has to go first in order to get positive 14 hours. So if I look at these denominators, this is x, this is 8x. Because this denominator is larger, it's going to lead to a smaller overall term. Thus, that one must go second when we take the difference of these two. So here's what I mean by that. We're going to get 1,200. And I should probably write this a little bit over so we can actually fit all this in. 1,200 over Rx minus 1,200 over 8x. And I'm just going to backtrack it, just make it a tiny bit neater. There we go, 8x. And then this is going to be equal to 14 on the right-hand side. Okay, something very important at this point. We need to identify the non-permissible values as well as the LCD. So maybe we do that up in the top corner here because, space is really tight on these problems. And so we're going to just utilize what we have. So our MPV is where x cannot equal 0, and hopefully x isn't equal 0, or else that means the train isn't moving and also the airplane's not moving. The LCD is the lowest common denominator. It's a product of all the denominators or the unique denominators, so we're going to write it as 8x. There we go. Okay, let's bring that back down here. Okay, now we're going to multiply everything by 8x, meaning I'm going to surround my left and right in brackets, and I'm going to write 8x on the outside. Now using distributive property, I'm going to multiply it into both. 8x times 1,200 over x is going to give us 8 times 12, which is 9,600, minus 1,200 times, or 1,200 over 8x times 8x. The 8x's are going to cancel, and this just becomes 1,200. Now on the right-hand side, we have 14 times 8, which is going to give us 112, and then the x goes with it. Now taking the difference of these numbers, we get 8,400, which is equal to 112x. Using some basic algebra from grade 10, we divide by the 112, which is the coefficient, and we're going to end up getting that x is equal to 75. Now, what does this mean? We want to summarize it right away. Therefore, the train is going 75 kilometers per hour. And then we can follow it up with what the airplane's going. The airplane is going 8 times as fast, aka 8x, which is equal to 8 times 75, which is the same as 600 kilometers per hour. So now we have the average speed of the train, the average speed of the airplane, given that distance here. And again, if you clearly define your variables in a chart or in a table, this is going to make it very, very effective for you. And so if you're not given a chart or table, just draw one out, a distance, speed, and time one, so that you can construct this all together. Okay, let's flip to another very similar problem, just with slightly different context here. So in example 3, we have a train that is scheduled to run 160 kilometers between two cities in Saskatchewan. We don't know what they are, but just two cities. If the average speed is decreased by 16 kilometers an hour, the run will take half an hour longer. What is the average speed of the train? So what they mean is that if we take this city 1 to city 2 and we look at one where it's a normal speed and then one where it's decreased speed, let's cover the following. We know that the distance between the two cities stays the same. It's not like the distance between the two cities changes at all when I change the speed. I still have to cover the same distance, so we got to go there. Now, the unaffected speed is just going to be x. The affected speed is going to be x minus 16 because we're the average speed but minus 16. In terms of time, we know it's distance over the speed in which it happens. So we have 160 over x. We have 160 over x minus 16. Now what we want to do is we want to put this together and say, well, if the difference between these two is 1/2, then we need to be thinking about it as what is the larger value of this fraction that would lead to that 1/2? If I take x and minus 6, it means the denominator gets a little bit smaller in this one. If the denominator is a little bit smaller, this term gets bigger, so we're going to use that as our first term here. I'm going to write that below here. This is going to be 1 over, not 1 over, 160 over x minus 16 minus, because we're taking the difference in order to get this time, 160 over x. And supposedly, if we take this distance over time or these two times and subtract them, we end up getting 1 over 2, or that it is a half an hour longer in order to go this slower speed. Okay, now a couple things we want to identify right away. Again, we want to do our non-permissible values. So maybe what we'll do actually here is, in your notes, there might be enough space, but I'm just going to move that down a little bit. And I'm going to write my non-permissible value. First and foremost, our one non-permissible value is x cannot equal 0. Our other non-permissible value is where x equals 16. If it's either 0 or 16, it's going to wipe out these denominators or eliminate them. And that means that we would have some sort of non-functional value, or this equation wouldn't make sense. In fact, it would be undefined. The other thing we want to do is write our LCD. So we're going to write LCD, or what we multiply both sides by. Remember, it's the product of all the unique denominators. So we're going to go 2 times x minus 16. We take one of each of these unique factors and make the product of them. Now, what does this mean we do from here? We surround our left, surround our right, and multiply it by the LCD. 2x times x minus 16. We're going to go 2x times x minus 16 on our left-hand side. We're going to distribute these terms to all of the unique terms. So we're going to go 2x times x minus 16 times 160 over x minus 16. That's going to make it 2x times 160, which is the same as 320x, minus, we multiply 2x and x minus 16 into our next term. This is going to end up causing the x's to go away, and we end up having where it is 2 times the x minus 16 times 160. And then the other side, our 2's are going to cancel, and we're left with x times x minus 16 as such. Now, what we're going to do here is we're just going to expand what we can here. So the 320x is going to stay the same, minus we have 2x times the 160. That's going to end up giving us negative 320. We have negative 2 times negative 16, which is 32. The 32 times 116 is going to give us plus, and sorry, there should be an x here, and then this is going to be plus 5,120. And then this is going to be equal to, on the other side, x squared minus 16x. Now, again, our whole goal is to make this into a quadratic equation so we can factor it. So I'm going to look at this and be like, well, my 320x's actually go away because they're plus and minus of the same term. And then on the other side, what I'm going to do is I'm going to move that 5,000 across. This is going to make it 0 is equal to x squared minus 16 minus 5,120. And then once we get it to this point here, we're going to factor it by inspection. This one's a little tougher. You might have to use your graphing calculator in order to get these zeros. We end up getting it when we factor it, x minus 80 and then x plus 64. Now, what does this mean for our 2x values? Here's what we have. We're going to have one of the average speeds is represented by 80. The other average speed is represented by x equals negative 64. Now, right away, you should be thinking, wait a minute, we can't have a negative speed or something that's going in some negative like this. And in fact, until we get to physics, we might deal with things that have negative velocity because that might infer some sort of directionality. But in this situation, or in Math 20-1, we don't think about it that way. So it wouldn't make sense to have a negative speed And so now we can summarize this and say, well, the speed that we did get that actually works, the speed. And I just want to make sure we actually answer it based on this. What is the average speed of the train? The speed of the train is 80 kilometers an hour. Perfect. And we just make sure to summarize that nicely. We put a box around it or highlight it if you have an available highlighter, and we're good from there. Now, let's talk about another one that's very similar, and it looks at this example, which we look at and say, well, a group of friends go on a 3-hour bike ride together. So there's a total time allotment that's committed to this overall trip. They ride 15 kilometers with the wind at their backs and then 15 kilometers into the wind on the way back. The average wind speed is 3 kilometers per hour. What is the average speed of the group of friends if there was no wind present? Now, here's how we solve this. First and foremost, they told us with the wind, we travel a total of 15 kilometers, and against the wind, we travel 15 kilometers. The average speed, if you have wind that is helping you or with the wind, that means there's a tailwind, it's pushing you along. We're going to take that x and add the 3 kilometers an hour that it would be pushing us. Opposite, if you're going against the wind or you're heading into the wind, this is a headwind and it affects you and it pushes you back. So it's going to be a -3 on our speed. Now, just like we've done before, time is equal to the distance we traveled divided by the speed at which we do it. We have 15 over x minus 3 when we're going into the wind. And then the total time was 3 hours. They said these two intervals happen within 3 hours. Now, what we want to do is set up our equations as following. So I'm going to go down here and write it as, well, first of all, we have 15 over x plus 3. We're going to add that together to make 15 over x minus 3, which is equal to 3, because the total times, or the time there and the time back, equals this overall 3 hours. Now what we want to do is we want to use our extra space here just to create an NPV statement. So we're going to write NPV where x cannot equal, it's going to be plus or minus 3 in this situation. Because if it's plus or minus 3, it will knock out that denominator, and that's not our intention here. The other thing we need to discuss is our LCD, and again, it's one of each of the unique factors. So x plus 3 is one of them, x minus 3 is the other. Now we have our terms that we can multiply to both sides here. So I'm going to scroll down here and go, well, bracket, 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 bracket. I'm going to multiply this one by x plus 3 and x minus 3. On the right-hand side, I'm going to do the same thing, x plus 3, x minus 3. There we go. Now we're going to distribute it to all the terms. If you see that the factor is the same for the LCD and the one in the denominator, it cancels. So we get 15 times x minus 3. And maybe I'll just write it out with the factor first. Then plus 15 times x plus 3, because the minus 3's cancel. On the other side, this is going to be 3 times the product of those two factors, which means it's going to be 3 times x squared plus 6x plus 9. And sorry, this is a difference of squares. So actually, it works out to plus 6x minus 6x and then minus 9. Now, let's expand this and simplify. When we expand and simplify, this gives us 15x minus 45. This is going to be plus 15x, and then plus 45 is equal to, on the other side, our 6's are actually going to cancel here, so we can wipe those out. 2 are the same thing. Now this is going to be 3x squared, and then 3 times 9 is going to be negative 27. Okay, now we want to make sure that this is a quadratic function, so I'm going to move all of the left-hand terms over. Before I do that, I can actually cancel out my 45's because they're plus minus of the same thing, meaning they're opposite operation. Now, I have 30 total x's on the left-hand side. I'm going to move them across. This makes it 0 is equal to 3x squared minus 30x minus 27. And the astute student in you should be like, hey, wait, there's an LCD, or not an LCD, but there's a common factor. There's a greatest common factor, or a GCF. I can divide all of the terms by 3. If I divide all the terms by 3, here's what it gives us. 0 is equal to x squared minus 10x and then minus 9. Now what I want to do is I want to factor this by inspection. And in fact, this doesn't actually work out to very nice numbers. You would either have to use quadratic function, or sorry, the quadratic formula, not the function, but the quadratic formula, and then get these values, or use your calculator. Some of you might think it's easier to use your calculator. If you end up using your calculator, here's the two values you end up getting. If you use quadratic formula, these will be the same. We get x equals negative 0.8 for one of the x-intercepts. The other x-intercept is x equals 10.8. Now, logically, there's only one answer here. The other one is extraneous. We're not going to have some sort of negative normal speed. Unless we're in physics and that's directionality, we don't consider this to be legit. So we say extraneous solution here, and therefore our only solution is going to be this 10.8. And we just want to summarize it with a sentence saying, therefore, the wind, or with no wind, and I'm just going to summarize it as they, because it's a group, they may travel 10.8 kilometers per hour, because we had a speed here. And I just want to make sure that the kilometers per hour is actually the units that we're dealing with here, because I did kind of go through that quick. Yeah, kilometers per hour is the speed that we're looking for. So again, just be looking for those extraneous solutions, because they do pop up, and you got to make sure that you're talking about the right things here, or else you can get steered off base quite quick. Okay, let's go to our next page here. So in example 5, to prevent grounding, a cruise ship anchors 18 kilometers away from a river port. To transport the passengers to the port, the crew uses smaller boats. So they don't want to get too close, because if they get too close, they could damage the whole side of the boat, or, it could cause risk to passengers. So they park 18 kilometers away and then take these small rafts. The smaller boats travel 12 kilometers downstream in the same time it takes to travel 8 kilometers upstream. So what that means is when you go downstream, you're getting helped by the current. If you go upstream, you're going into the current and it's affecting you. So what we want to do is, they say if in A here, the speed of the current is moving at 6 kilometers per hour, let's write some expressions that represent the speed upstream and downstream. First of all, let's talk about downstream. We're going to say x plus 6 kilometers per hour represent the speed downstream. And again, the reason we say it represents the one downstream is because when you are adding speed, it means you're being helped. And when you go downstream, the current is pushing the boat down the stream. So we consider this to be a positive in terms of our extra velocity or extra speed. And then we're going to say let x minus 6 kilometers per hour represent the speed upstream instead. And then again, the reason we consider this to be upstream when it's negative is because if you go upstream, you're having to fight the current. You're going against it, so it's impacting your overall speed, and we consider this to be kind of a hindrance to motion rather than something that's helping. Now, what it says is, if we consider the instructions above where it says, okay, now we have these definitions of the different speeds, calculate the total time it takes for the small boats to travel upstream, given that this is the circumstance, or more specifically, that we have the following information given to us with our now clearly defined variables. They say that traveling this distance downstream takes the same time as it does upstream. I think that's a very, very important thing to note. And especially in these types of problems, it's really important to just highlight that information, because now what we can say is, in our calculations here, we can say that if time is equal to the distance over the speed at which it's covered, and we know that this is the same for both boats, or same for both directions, we should say, then if it's the same, then the time 1 will equal time 2. And if time 1 equals time 2, we're going to create a ratio where it was 12 kilometers upstream divided by the speed at which it does it is equal to the 8 kilometers upstream divided by the speed at which it goes upstream. Now, in this situation, you have two options. You can use the LCM, or the LCD, I should say. LCM, similar concept, but we can use our lowest common denominator to get rid of these denominators. Or what you could realize is that when we cross multiply, we're actually doing that same thing. So maybe just to formalize it for this unit, what I'll do is I'll show it using the LCD method and our MPVs. So first and foremost, we would go MPVs are where x cannot equal plus or minus 6, because if it's plus or minus 6, or the speed matches the current, then the boat's not going to move. The other thing we want to state is our lowest common denominator, and again, it's the product of the unique factors. So if it's x minus 6, x plus 6, we need to see at least one of those. Now what we're going to do is, on both sides, surround them in brackets. We're going to multiply by this LCD, so x plus 6, and then here's where I potentially want to move this information over, or even just move it up here. I'm fine with it being moved up. We're going to multiply it by our x plus 6, x minus 6. On the left-hand side, we're going to do the same thing, x plus 6 and x minus 6. There we go. It gets multiplied into both. And again, this is why cross-multiplying works. Do you notice how the opposite term is the one that remains? If I cancel out the terms here, x plus 6, x plus 6, x minus 6, x minus 6, I could realize that I could have just cross-multiplied by the opposite denominator. But again, if you want to show this formalized step, I think this is a great idea. Now we're going to multiply this through, and this is 12x. 12 times 6 will end up giving us the 72, or more importantly, the negative 72, is equal to 8x. 8 times 6 is going to give us 48, and it's positive. And now what we want to do is isolate this for x. I'm going to take the x's from the right-hand side and move them over, which will give me 4x on this side, is equal to, I'm going to add 72 to the other side. 48 plus 72 is equal to 120. Then from here, I'm going to divide both sides by the 4. When I divide both sides by 4, you're going to easily recognize that x will be equal to 30. Now, you're like, wait a minute, what is this representative of? We have an x equals 30, and that's supposed to tell me something? Well, remember, what does x represent? It's the speed in still water. It's the unaffected average speed of these boats if there was no like kind of current pushing or pulling the boat here. Now, what did they actually ask for? They asked for something very specific. What is the amount of time it takes to travel upstream from the cruise ship to the port? And so what is the total distance that needs to cover? In this situation, they gave us a comparison of time, but they told us that the cruise ship is 18 kilometers away from the river port. So we're going to use that information and now this new speed to help us out. The time it takes to go upstream, given that we have this overall speed and that we have this distance it needs to cover, there is 18 kilometers this boat needs to cover, and it needs to do it with a speed of 30 kilometers and then affected by the 6 kilometers per hour. Because if we're going upstream, remember, we're fighting it. We're going, like, we have to travel this 18 kilometers, but we're getting pushed against the whole time. Now, this is going to give us a time upstream of, we get 18 divided by our 30 minus 6, which is the same as 18 divided by 24. 18 divided by 24 is a reduced fraction, is 3 over 4. And this means it takes 3 over 4 hours, or 3/4 of an hour. And so maybe I'll just say 3/4 of an hour like this, to go from the cruise ship to the port. Perfect. And we'll highlight that and we'll make sure that's good. Now, this one was a little bit tricky. And the reason it was a little bit tricky is because we had to go back to the original information given. And instead of dealing with the 12 and 8 kilometers that they gave us, that was purely just to compare certain intervals that can be traveled in a certain amount of time. Once we have that overall speed that the boat can travel overall without a current, then we can use that in this second piece of information. So maybe what I'll do here is just provide a little bit of an arrow being like, hey, there's step 2 there. All right, now here's where we go to kind of the ones that I really, really like, which are the sharing tasks ones. Not that the other ones are not valuable, but I really like these ones too. So if we deal with sharing tasks, here's how they're going to kind of go about. You're going to have some sort of comparison of how people can complete a job or how they can complete work together. Now, in this specific situation, they say that Emily takes 4 hours to paint a room, while it takes Selena 3 hours to paint a room. How long will it take them to, how long will this paint job take if they paint it together? So rather than Emily working hard away and doing it for 4 hours and Selena individually working for 3 hours, they could work together and reduce the total amount of time they spend. Now, here's what we need to fill out here. Time it takes to paint the room? Well, it was 4 hours for Emily, it was 3 hours for Selena. How much can they do in 1 hour? It's 1 hour over the 4 hours that it would normally take. It's 1 hour over the 3 hours that it would normally take. So this should make sense, right? Because if it takes Emily 4 hours to paint a room, in 1 hour, she could only do a quarter of that work. Now, what is the fraction in t hours instead of 1 hour? We're just going to write it as generically t over 4, meaning the hours that in whatever, maybe it's half an hour, 3/4 an hour that she can do, is that 3/4 or whatever this value is divided by the 4 hours it would normally take. And same thing for Selena, we're going to write it as time over the 3 hours. Now, in this situation, we have two different methods we could use here. Method one, we're going to compare their individual rates to a total job being done. And here's what I mean by that. We can write it in the following way. We can write it as time divided by the 4 hours plus the time divided by 3 hours is equal to the one job being completed. Now, I kind of want to annotate this here. This is the time together. So if I point up to the top here, we consider this to be time together as such. And then in the denominator, this is considered to be their individual effort. So I'm going to write it as individual. So we have time that it would take them together divided by their individual rates equals the job being complete. And that's what this one is representative of. It's saying a job is completed. Perfect. Okay, so now that we know it's a ratio of their together time over their individual rates, which then added together gives us a job complete, we can use the LCM here in order to eliminate terms and get this in terms of some sort of specific value. To do this, we look at the denominator and say, well, if I look at this one, the LCD, which I'm going to write above here, is 4 times 3, which is the same as 12. Now, there's no non-permissible value because they're both just integer values, so we're good there. I'm going to multiply everything both sides by 12. And so maybe we do that in green here. I'm going to multiply and multiply. I'm going to multiply this side by 12. I'm going to multiply this side by 12. If I multiply both sides by 12, 12 divided by 4 is 3t, plus we have 12 divided by 3 is 4t, which is equal to, on the other side, 12. I add up their collective t's is 7t equals 12, and therefore we get t is equal to 12 over 7, which t is equal to 1.7 roughly. And this is 1.7 hours. So this is that collective time that if they were to work together instead of working individually, it would take them 1.7 and 5 or 1.7 hours instead of 4 and 3. And that should make sense, right? If you work individually, it's going to take you a lot longer than it would if you were working with another person collectively. Perfect. Okay, method number 2. This is to use the distance equals speed times time. Now, to do this, when we look at this here, we know from previous that our time is equal to the total distance divided by the speed at which we can do this. Well, in our case, the distance is one job being completed divided by the time it takes for them to complete a job in that one given hour. Now, this is going to be equal to, if we do our reciprocal rule, 1 divided by, in the brackets, we take 1/4 plus our 1/3. We know by the reciprocal rule here that this would be, and I'll just continue it off to the right, this is 1 divided by, I'm just going to combine these fractions together actually. It gives you 7 over 12. If we take this one step further, it's 1 times 12 over 7, which means that the time taken is 12 over 7, which is equal to 1.7 hours. So regardless of which way we do it, we end up getting the exact same solution here for them working together. Now, if I had to pick a direction of which way to go in this problem, for sure it would be the method 1. I think it's more intuitive, it's more connected to this unit. If you look at the one in method 2, that's more of like a physics approach to it. And, I think it might be tough to kind of draw those parallels to the unit if we're doing it in that given way. And again, with this one, these sharing tasks, you're going to see in one of the next problems here, we actually can do this in a slightly different way that's technically the same thing here. So in example 7, I want you to hold on to this idea that sharing tasks are always a ratio of things happening individually to something that is happening collectively. And the way we did this one can be one way. The way we do our example 7 is just going to represent it in a slightly different way, but I'm going to try and create that parallel for you here. So let's move into example 7 so I can show you what I mean. Mark can weed this garden working alone in 90 minutes. Shelby can weed the garden working alone in 75 minutes. If they work together, how long will it take them to weed the garden as a collective unit? Now, here's what we can do in this problem. And this is, I'm going to kind of go method 1, method 2 in this situation, but they actually are the same thing. And here's what I mean by that. Let's say I go method 1. Sometimes I like to describe these problems in the following way, and this will constitute method 1. Let's say I create a ratio of individual effort. One job can be completed in 90 minutes by Mark. So if Mark wants to weed it alone, he can complete the one alone in 90 minutes. Plus 1 over 75. Shelby can complete one job in 75 minutes. This is going to be equal to, if you add up their individual efforts, the collective time it would take them, or one job being completed in X amount of time. And so I'm just going to annotate all that in here. This one and this one, these are considered to be the individual efforts. Over on the right-hand side, this is considered to be the together effort. And then on the numerators, this is a job being completed. So what I'm going to do is I'm just going to kind of like arrow this way, and I'm just going to connect a bunch of arrows in here. This is the job being completed. Perfect. Now, if we were to solve this, here's how we would end up solving this. We look at this and we say, well, the LCD in this situation, let's maybe, you know what I'm going to do is I'm going to shift all of this slightly down. I know that might be an inconvenience for your notes, but I'm going to shuffle it down and be like, the lowest common denominator is going to be 90 times 75 times x, because it's one of each unique factor. And you can multiply the 90 times 75 and get a value. That's totally fine. If I multiply all these terms by that LCD, so I'm going to go everything on my right, everything on my left, 90 times 75 times x, and this is going to get multiplied to everything. Well, in the first term, the 90 is going to cancel, and this is going to end up giving me 75x, plus our 75 is going to cancel, leaving me with 90x, which is equal to my x's cancel, and I get 90 times 75, which is the same as, and actually maybe let's just write it out just so we can visually see it. This is going to be equal to, on my left, 165x's if I combine them together, which is equal to 90 times 75, which is 6,750 or 6,750. I divide all sides by the 165 or the 165, and this ends up giving me that x is equal to 40.9. So it's a bit of a decimal, which is okay. Now, what does this mean in the end? It means that collectively it takes them 40.9 minutes if they work together. So I'll make a summary about that. It takes 40.9 minutes to weed if Shelby and, I want to make sure I get his name, yep, Mark, work together. Okay, great. There's method one. Now, all I'm going to do in method two is just change the formatting of the original statement to match what we did in example 6. And then I'm going to explain how they directly compare. So realistically, I'm calling them method 1 and method 2, but they're just variants of each other. So I'm going to write it as method number 2. Here's how we're going to consider method 2. Instead of thinking about it as a job complete over an individual rate, job complete over an individual rate equals the together collective rate, what we can do is we can create a ratio of times as a together over individual, which will allow us to complete one job. How do we do that? Well, instead, I can rewrite this as the following. X time that they could complete the job together divided by the 90 minutes that it takes Mark, plus X divided by the 75 minutes it takes for Shelby to complete individually equals one whole job being completed. So in this situation, I look at this and I'm like, okay, let's let X be the time together. If X is their time together, we're saying if they work together, it's a ratio of their together time over Mark's time, plus a ratio of their together time over Shelby's time. And if we add those two ratios together, we end up getting one job completed. And so let's annotate that all in here. So these top ones, these are the denominators. They're my individual effort. X, let X be the time together. And I'll just short form it as together. And then on this side, or our right-hand side, this is a job being completed. Perfect. Now, how did I get from method 1 to method 2? I want you to notice one thing right away. Do you see how the x is in the denominator here? In order to get the 1 in method 2, all I did was take the x and multiply it to both sides, which then made x go to the numerator here, x go to the numerator here, and it gave us a statement where x's were in the numerator on the left, and we were left behind with just this 1 here. So regardless of which way you set this up, if you want to go method one or method two, it's going to isolate the exact same way. Because now if you did your LCM, you would end up getting 90x plus 75x equals 90 times 75, and it would give you all the same setup. You just need to choose a direction that makes sense for you. I really like this one where it's, hey, a job is being completed, but individually it's being completed in this time. A job is completed individual time here. And if I put these two together, it gives me a job being completed over the together rate. I like that approach, but some of you might say, oh, I like it where it's like a ratio of the individual and collective time, a ratio of the individual collective time equals a job being complete. You just choose which direction you want to go. Both are totally fine. In fact, they are the same equations. So you just choose and go with it. All right, let's do one more example here. Two hoses fill up a swimming pool in 3 hours. It would be bad if horses are filling this up. Two hoses are filling up a pool together and they do it in 3 hours. If only hose A is used, the pool fills in 4 hours. How long would it take to fill the pool if only hose B were being used? Now, what we're going to do in this method here is, or in this problem, is we're going to use that second one we kind of talked about here, where in method two, it was a ratio of times that allow us to complete a job. Now, we could use this one here, but let's just show that we can use this one because we didn't technically use it, and we're going to now apply that. Now, we have used it in example 6 as well, or what I mean by this is method 2, but let's use it again just to see if this works. So in this problem, we have two hoses filling a pool, and they can fill it together in 3 hours. So I'm going to write it as the following. 3 hours divided by the individual rate of hose A, which was 4. Then we're going to add 3 hours, again, because this is the time together, divided by the amount that hose B could fill it in, which we don't know yet. And supposedly, if we add these ratios of the together time over A, together time over B's individual rate, we would end up completing one full job. Now, let's make sure we annotate all this. Here on the left-hand side, we're going to say that these two are the individual rates. Perfect. In the numerator, these are the collective rates, or this is what they can do together. And so if you want to just short form it as the together time, I think that's a great idea. And then on the right-hand side of the equation, this is a job being complete, or you can just simply short form as job complete. Because obviously, if you add their two efforts together, you should finish the job. Okay, now what we want to do is off to the side, maybe we state our LCD, and we can do that anywhere. So maybe even on the right-hand side, we're going to go LCD, or lowest common denominator. It's the product of the unique factors, which are 4 and B. I'm going to multiply both sides by 4B. If I multiply both sides by 4B, here's what it looks like. Put terms around, it's going to be 4B. And, maybe just to avoid some overlap here, I know we've been doing this on the past couple problems. Maybe I rewrite this just so that we can keep it all neat. So 3 over 4 plus 3 over B, which is equal to one job being complete. I'm going to multiply both sides by the LCD, which in this case is 4B. There we go. And then again, we could technically, if we wanted to, just before we continue here, we could write an NPV and say that B cannot equal 0, or that the rate of which the hose from B is filling the pool can't be 0, but hopefully it shouldn't be 0. This is like saying that hose B would be doing no work, and hopefully it's not doing no work to fill the pool if we're looking for an individual rate, or else that would mean it's all on A, and A would be the thing filling it in 3 hours. So you could write this, but in these word problems, it's not necessarily as important because hopefully the takeaway is fairly obvious, but for consistency, sure. Now, 4 divided by 4 will leave us with just the B. This becomes 3B plus 4B over B is just 4. 4 times 3 is 12, which is equal to 1 times 4B, which is 4B. If I subtract away the 3B from both sides, as such, there we go. This is going to give us 12, which is equal to 1B. And then therefore, B is just equal to 12. So now we can summarize it and say, therefore, hose B can fill the pool individually, or you could say alone, but maybe I'll just say individually, in 12 hours. So what this means to me, at least, is when I read back on this problem, I'm like, well, it only took hose A 4 hours. So what we could say is like maybe one's a fire hose and the other one's like a garden hose. Hose B could be like a small little garden hose that's just meant to like water plants, whereas hose A could be something like a fire hose that can have a larger rate of volume flowing through it, so therefore it's a lot quicker. And don't be thrown off by times in these, or don't be thrown off by data. As long as your setup is good, don't worry if those values are quite large, because I know that that can sometimes stump students and say, well, in real life, like it's not going to take 12 hours to fill a pool. What are we talking about? But you want to sometimes just avoid thinking about things too logically, or else it's going to take away. Now, that's ironic because we began the lesson saying you got to think about things logically when you report on them, but just try to, as long as your setup is good, if some of the problems give you slightly larger values than you might expect, that's okay. Just make sure you double check and everything logically makes sense. In this situation, if they gave us -12, I'd be like, wait a minute, -12 hours, that's not a thing. We would say it's extraneous. But for this one, 12 hours, we're like, that's okay. All right, here's where you want to go into your assignment for part 2. I definitely recommend trying some of these out because logically, these do take a bit of effort and some practice just getting your head around them. All right, good luck on your practice.